in Max Planck Institute for Physics in Munich, Germany. And he will present some result studies on multi-wavelength observation of active galactic nuclei. The floor is yours.
Thank you very much, Massimo, for the nice introduction, and thank you for this nice opportunity. I'm really happy to be here, and today I will talk about particle dynamics and acceleration in AGN jets using observations of bright blazars. The results that I will show are a bit biased towards results that I obtained within the MAGIC collaboration, because it's the experiments and the instruments with which I am the most involved at the moment. So I apologize for that if there's this bit of bias. So, okay, just to start as a brief introduction, I think the audience is already quite familiar with that. So what are active galactic nuclei? They consist of a supermassive black hole of millions to billion solar masses that is accreting matter, forming a hot accretion disk. And in about 10% of those AGNs, we see a huge structure, relativistic plasma jets on kiloparsec to megaparsec scale. And in those jets, we have detected non-thermal emission throughout the entire spectrum up to TeV energies. Those jets have basically been resolved through the entire spectrum from radio to X-ray, and also since recently at very high energy. This was published by the HES collaboration in the Centrus A. And if you do some back of the envelope calculation, assuming that most of the emission up to the X-ray comes from cyclotron radiation, then you need electrons with Lorentz factor of 10 to the 5, 10 to the 6. So almost TeV electrons in those jets. So jetted AGNs are extreme particle accelerators. In this talk, I will mostly focus on blazars, which are jetted AGNs that are observed at a small angle relative to the jet's axis. And because of this small angle, there is a strong relativistic beaming of the emission, with Doppler factors roughly equal or above 10. So the observed emission is strongly enhanced by a factor of Doppler to the 4 with respect to the intrinsic emission, and also the time scales are shrinked by 1 over delta. One of the main characteristics of AGNs is that they are variable throughout the entire spectrum and of all time scales from years down to minutes. So if you want to understand AGNs, there are two crucial ingredients that you need to consider. Is on one hand, dense time-wise monitoring, and also to organize simultaneous observation throughout the entire spectrum. And despite the fact that we have been observing blazars since decades now, there are some fundamental basic questions that remain to be answered. For instance, particle acceleration, the structure of magnetic field, which would be the two main topics that I will touch in this talk. But there are also some open questions regarding the jet launching mechanisms, the composition of the jets, what particle species do we have in those jets, what is the origin of the fast spectral and flux variability that we see, and also the origin of the gamma ray emission. Now, from a broader perspective, blazars are also essential to study in our current era of the multi-messenger astronomy. For instance, they are considered as potential sources of 10 to the 18 and above cosmic rays, which are believed to be from extragalactic origin, but we still don't know where they are coming from, those cosmic rays. And they're also potential candidates for PeV neutrinos that are detected by IXPE. So the MAGIC telescopes, because of these big open questions that remain to be answered, the observation of AGNs is one of the prime scientific program of the MAGIC telescopes, which are two 17-meter diameter giant telescope on the island of La Palma. Probably you have already heard of those two telescopes. Basically, what we do is to observe the shrink of lights that are emitted in particle air showers that are produced when we have a primary gamma ray interacting with our atmosphere. And based on this shrink of light, we can extract information on the particle, the gamma ray initial energy, and also separates from a very big background of photon cosmic rays. So with this technique, the atmospheric air shrink-off technique, we cover an energy range from 15 GeV to 100 TeV, roughly. We have an energy resolution of 15 to 25%. It depends a bit on the energy at which you're looking at. We have a field of view of 3.5 degree, and the angular resolution is 0.05 up to 0.1 degree. And in my work, I'm mostly focusing on these two blazars, Maclaurin 421 and Maclaurin 501. Why? Because there are two big advantages. They are bright sources, meaning that we can easily detect them throughout the entire spectrum of the TeV energies with the current instruments. When I say easily detectable, I mean that they can be detected within a few hours or less with magic. So each night we get a positive detection of the source, independently of if the source is in a high activity or in a low flux emission state. And also they are nearby, meaning that their gamma ray emission is not strongly absorbed when it interacts with the optical infrared background. And because of these two big advantages, we are performing variability studies on short time scales to quantify and try to understand the particle acceleration and cooling, and also perform some intra-band correlation. So what we do with those two sources, we perform some so-called unbiased monitoring. So we observed every 2-3 days, so with the regular cadence, independently of if the source is in a bright or high activity state. And we coordinate the magic observation with a large sample of other instruments, more than 10, to achieve a simultaneous radio to very high energy coverage. And because they are bright and nearby, those two sources are also among the first sources that are observed by new instruments that are launched in space. And one of the recent examples is the IXPE satellite that was launched in 2021. And the first blazars that IXPE observed was Maclaurin 501 and then Maclaurin 421. And in this talk, I will focus a lot about this joint magic and IXPE observation that we performed recently. Okay, so just to give you a rough idea of the amount of data that we collect and use for our studies, I'm showing here two multiwavelength light curves of two recent papers from Maclaurin 421 on the left and Maclaurin 501 on the right. And you can see that we usually work with data throughout from radio to TV, and also including polarization in the radio, optical, and since recently in the X-ray. So one thing that we do with those multiwavelength light curve is also to try to quantify the correlated variability between the different bands. And what pattern that we usually and very often see is a tight correlation between the very high energy and the X-ray emission. And this happens independently of flares or low activity. So it's an intrinsic behavior of the source. And what we can tell from that is that we have a single particle population that emits in the X-ray and very high energy. And currently the simplest scenario to explain those correlations that we see is to consider the so-called tectonic model, where you have the X-ray that is radiated via electron-state photon radiation, and then the same electrons produce the very high energy emission via inverse Compton scattering. We also see some strong dependence of the correlation slopes when you split the two energy bands into sub-energy bands. And this is again consistent with the so-called tectonic models, possibly due to the change of the cross-section of inverse Compton scattering throughout the energy. So leptonic models works well. Here's a fit of a leptonic model to multiwavelength data, but I should also mention that the story is not fully closed. hadronic models where you invoke protons interact with the background low energy photon fields that will trigger some secondary particles that will subsequently produce gamma rays when they decay, or simply proton synchrotron. These kind of scenario are also able to describe the SED. So the picture is not yet fully clear, and in particular recently when IceCube measured some neutrinos from this blazar TXS0506. In order to explain those neutrinos from IceCube, you need to invoke at least a subdominant proton population. I should, however, mention that in some cases, hadronic models can be challenging due to the energetic, because protons are much more massive than electrons. So now going a bit into the question of particle acceleration in AGN jets. So jets of blazars, they are, or jets AGN in general, they are a huge structure, and you can have some acceleration of particles at multiple places in the jets and also through different mechanisms. Currently, one of the most efficient acceleration mechanisms that are thought to be at play here is, on one hand, diffusive shock acceleration, where you have a plasma disturbance propagating in the jets, and particle can bounce back and forth on this shock wave. And through this process, you get a systematic energy gain of the particles. And the second process is magnetic reconnection, where the field lines in the jet reconnect, they're reordered, and through this process, you have a release of energy from magnetic energy to kinetic energy. So the question is how to disentangle them, and because they affect the magnetic field structure very differently, one very potential promising probe is polarization, and in particular the measurements of the polarization in the synchrotron spectrum. The synchrotron emission is strongly, mostly linearly polarized, and the polarization angle will be oriented perpendicular to the magnetic field lengths. Additionally, if you assume in a perfectly ordered magnetic field structure and parallel of electrons in this magnetic field, then you expect the maximal degree of polarization that is this formula, and if P is roughly equal to 2, as often observed in astrophysical sources, then you get a maximum expected polarization degree of 70%. And if you have some turbulence, then this number will decrease. So by measuring both the polarization degree and the polarization angle, you can learn about the structure of the magnetic field and how disordered is this magnetic field in the source. Regarding diffusive shock acceleration or Fermi acceleration, you expect, this is also seen from simulations, that the shock will trigger some magnetic field that is perpendicular to the jet axis. So it will kind of compress the magnetic field lines. And because of that, the polarization angle will be parallel to the jet axis. So you expect, if shock acceleration is at play, you expect the polarization angle parallel to the jet axis, and it should be the same throughout all frequencies in the synchrotron spectrum. Close to the shock, the magnetic field will be strongly ordered, so you expect a high polarization degree, and then particle will advect away, downstream the shock, and populates a region that is broader, larger, affected by more turbulence, so the polarization degree is expected to decrease with energy. And you also expect a low variability in those properties of the polarization. Regarding magnetic reconnection, here the picture is very different because you have a complete reordering of the magnetic field structure. We expect strong variability in the polarization degree and the polarization angle. The polarization degree should be roughly comparable among energy. Here you can see some simulations on the left-hand side. The black curve is the X-ray polarization, and in red is the optical polarization degree. And regarding the polarization angle, it can be oriented throughout in any direction with irrespective of the jet's axis, and they can decouple between the different energy bands. So IXPE started to observe in 2022. And if we come back to the two sources that I mentioned at the beginning, Maclaurin 421, Maclaurin 501, in this energy range of IXPE, which is roughly from 2 to 8 keV, we are probing the falling edge of the synchrotron spectrum. And this part of the SED is emitted by a synchrotron radiation by the most energetic electrons in the jets. So we are really probing the magnetic field that is affected the most energetic particles. And there is an important synergies here with MAGIC, because as I was mentioning, we see a tight correlation between the X-ray and the very high energy. So if we want to have a full picture of the emission and the acceleration process, combining IXPE with MAGIC is absolutely crucial here. So the first campaign that we organized was on Maclaurin 501 between March and April. We had 3 IXPE observation, and we organized simultaneous MAGIC observation. And what the IXPE data showed is that the polarization in the X-ray is around 5 to 10%. And this is about a factor 2 to 5 higher than the optical. So there's a strong energy dependency here. Regarding the jet axis, it is well aligned with what we see in the optical and the radio, and it was also fully variable. Regarding 421, here the behavior is very similar. Again, the strong energy dependency of the polarization degree, 2 to 5% higher in the X-ray with respect to the optical. And also the X-ray is roughly parallel to the optical and radio bands. And during those observations, the two sources, Maclaurin 421 and Maclaurin 501, were probed in a low activity. And later I will show results of these campaigns when the source was in a varying states. So if I come back to the original acceleration mechanisms that I described, these behavior that we see here tend to favor, first, we have an energy stratified region. So electrons, the most energetic electrons emit the X-ray close to the shock, and then we have a broader region dominating the optical and the radio. And the polarization properties also hints towards a shock acceleration process, at least during quiescent activity. We computed some correlation between the very high energy and the X-ray, and we do see a 4 sigma correlation between the X-ray and very high energy emission without any time lag. So this is not outstanding results on its own, confirms previous studies, but it allows us to claim that the very high energy photons are very likely emitted close to the shock front, where the X-ray is coming from. I mentioned earlier that the polarization properties did not change a lot. This is not completely true, because in June 22, what IXPE observed is a systematic rotation of the polarization angle. It rotated by 360 degrees roughly over 5 days in a roughly systematic manner. The IXPE team tried to understand if it was compatible with random walk, so some stochastic process, and it was excluded by roughly 3 sigma. So it doesn't seem to be only caused by turbulence here in the magnetic field, and rather what they propose is that this rotation is possibly caused by a shock that is rotating within the jets on helical field. And then you don't see a rotation in the optical and radio bands because this region is much larger and not affected by this small-scale rotation in the jets. Unfortunately, we could not observe simultaneously with MAGIC, but what we did is to schedule some new star observation. On the top, you can see the light curve that we collected with new star. And there was some flux variability during these observations. But what was mostly interesting is that when we plot the X-ray spectral index as function of the flux, we see so-called hysteresis loops. Hysteresis loops, which, as the name states, some loops in the parameter space. And there is first a clockwise direction loop. So when the flux increases, the spectrum is harder than when it decreases. And then we had also a counterclockwise loop. This is the opposite. So when the flux decay, the emission is harder than when it rises. These patterns are very powerful to make some constraints on the acceleration and cooling processes at play. For instance, for clockwise loop, they are indicative of a low energy lag with respect to the high energy emission. So the highest emission cools first, and then the lower energy comes later, decays later. And this suggests that we are in a system where the variability is driven by synchrotron cooling. So the acceleration timescale is significantly lower than the synchrotron cooling timescales. And regarding counterclockwise loop, we're in the opposite situation. We have a high energy emission that is lagging behind the low energy emission. And this occurs typically when the acceleration timescales are roughly similar to the cooling timescales, because particle still gets accelerated. So within a few hours, we have strong changes in those timescales, acceleration and cooling. And this strongly suggests that the acceleration evolves, acceleration efficiency evolved during the rotation, possibly caused by a slower decay in the velocity of the shock in the jets during this rotation. So as I mentioned earlier, in 2022, we mostly observed the Macarians in a low activity. But as you know, during flares, blazars can show very strong spectral variations. And these spectral variations directly imply that we have some very important impacts of the acceleration. So IXPE here would be really important to disentangle that and understand the origin of flares that remains quite elusive phenomenon. And we got lucky in December 23. We organized it was a pre-organized campaign with IXPE and MAGIC. And during these campaigns, the flux was quite high at very high energy, about 4 times higher than the average flux for Macarians, 4:1. You can see with a dashed line the quiescent flux for Macarian 4:1 at TV energies, and in blue is the measurement. So flux was clearly above. And interestingly, during this flare in the gamma ray, there were strong variations in the polarization degree and also in the polarization angle. So if we zoom a bit in the polarization degree, this is what we see. Oops. Okay. No, it's okay.
I think they want to change the slides. Not sure.
It works. I think it's only the laser.
Okay.
Well, you can see on the left hand side, it's a plot of the ratio of the polarization to the one measured in the optical. So in gray, it's the IXPE measurements in 6 hours bin, and in black is the IXPE measurement in 12-hour bin, and in blue is in the radio. So you can see that at the peak, we have X-ray polarization that is close to 10 times higher than what we have in the optical. So it's strongly chromatic here, but it strongly varies over time on less than a day time scale. Regarding the angle, there is some variations here that seems to be completely erratic without coherent behavior. We checked for correlation between the polarization angle, polarization degree, and also with the flux. This is checks that we did, and we do not see any coherent pattern here. It seems to be quite random. Let me, however, mention that these changes in the polarization angle seems to be always within 50 degrees from the jet axis. And when you compute the average of the X-ray polarization angle, it aligns quite well with the jets. So possibly there's still some ordering there happening, possibly caused by a shock we checked also for correlation between the X-ray and very energy fluxes. We see some hints, but there is quite some scatter in the measurements, possibly suggesting that several source parameters changed during this flare. And we verified that also with a dedicated modeling of the broadband SED, with electronic modeling of the broadband SED, and we found that the magnetic fields, particle density, and also the radius of the magnetic field of the emitting zone had to change throughout the flare. So overall, what we came up with a scenario to explain these flaring episodes with IXPE is that the fact that the average X-ray polarization angles remains well aligned with the jet axis indicates some ordering of the polarization of the magnetic field, so possibly caused by a shock. And also we have a strong chromaticity, well in line with shock simulations. Regarding the variability, we ascribe that to magnetic turbulence. So before crossing the shock in the jets, possibly the plasma was strongly turbulent, and this is what causes the variability. And this is also in line with the, maybe you know this model from Marcher, the turbulent model from Marcher, TMZ model. And the numbers goes quite well in line with what he predicted in his model. So that's what we ascribed to this polarization variability. I should, however, mention that magnetic reconnection is not fully ruled out. We cannot claim that yet. And I believe that more plasma simulations here are needed. We are possibly only scratching the surface here, so more theoretical work here is needed to really quantify and disentangle the two acceleration scenario here. That may also possibly take place simultaneously. So this brings me to my conclusions. So Maclaurin 421, Maclaurin 5.1 are ideal tools to understand the particle dynamics in AGN jets in general. We see some complex variability behaviors, and thanks to IXPE, a new window was opened to understand the structure of the emitting region. So we now have a strong indication that the emitting region must be energy stratified. The data so far seems to go well in line with shock acceleration, and the recent data during the flare also highlights the important role that turbulence can play in the flares. And I should mention that this is only the first data set during a flare of a blazar. So we are very likely just scratching the surface, and future observation will be essential to confirm or not that what we see is something common or was something very special and will not repeat often. And thank you very much.
Thank you very much for this nice overview on these exciting results on these two blazars. Any questions? Maybe also from remote.
From remote, and what? Yes.
All?
How many more marked blazars are available for such kind of studies, both in terms of magic and plus LST1 and IXPE?
So for if you want in terms of X-ray brightness, Maclaurin 421 and Maclaurin 5.1 are the brightest, and they are the ideal sources that you want if you want to check variability in the X-ray polarization. I mean, IXPE observed other blazars, but because they are fainter, it's much harder to check this kind of variability, given the sensitivity of IXPE at the moment.
So the limiting instrument here is more IXPE.
I mean, if in the very high energy band, we are also limited. I think there's a few with the current sensitivity. There's a few more targets with respect to IXPE in which we can search for strong variability in the order of 10 sources that we can detect on a daily basis. But here, because they are the nearest blazars and because they have been observed over decades, keeping observing them will always give us the possibility to compare with the ultraviolet data. So that's one advantage too for the materials with respect to other sources.
Yeah, thanks a lot for the nice podcast. So concerning the magnetic reflection scenario, if I remember correctly, our law of the field particle distribution would be harder than the one that we get from the diffusive shock acceleration scenario, right? So can we use this also to try to disentangle the
So the slope of the slope in magnitude connection will depend on the magnetization of the region. So you can play with that, and indeed it can be harder. However, there are studies which shows that you can easily access a power law of even 1.5, 1.8 in shock acceleration. So only the slope is not that easy. Although we did some modeling for Magellanic 501, and we found during this campaign, and we found a slope of 2.3, which is the classic expectation of relativistic shocks. But based on the slope, you can also have this 2.3 slope in magnetic connection.
Oh, okay.
So it's not a discriminating factor.
And also a couple of curiosities. So somewhere you mentioned that from the variability you get an estimate of your dimensions, and you mentioned Schwarzschild radius. But actually, do you get also information on the distance from the black hole? Can you locate that? So the variability is probably the dimensions of the size of your emitting zone. But what about the distance from the black hole? Or you cannot distinguish between nearby or far away from the black hole.
So we do not have the angular resolution as in the radio to do that. What you can do is to use an opening angle assumption on the opening angle. Then you know roughly the size of your source based on the variability timescale, and based on this opening angle, assuming that the region takes the full jet's cross section, then you can try to place constraint on the location.
And what do you find?
It's 10 to the -2, 10 to the -1 parsec, roughly.
Okay.
It depends on the size of the emitting region. Then
Okay. Hundreds or thousands.
in typically parsec, 10 to -1. Yeah.
10 to -1, -2 parsecs.
Yeah.
Fraction of a parsec.
Yeah.
So hundreds or thousands of Schwarzschild radius.
Then if
So
you
it won't be located very near the accretion disk. It's more distant.
for typical variability timescale of day, no. From this calculation I mentioned, it possibly further. But if you look at FSRQs, which you assume some broadband region that can absorb the gamma ray emission, if you place some constraints such that there is no strong absorption, then you can start a bit playing the game. Where should I put my emitting region in the jets to limit the absorption of the gamma ray emission? Okay. And there has been studies using Fermi-Lat data only, not in the broad energy band, and most of them seems to be beyond the broad line region.
Okay, the broad line region. Maybe related to this. The comment from you on the association between the blazar, the PXS, something, and the neutrino detection. Do you think it's a strong evidence for this connection or not? What's it really?
So I would say that the ice cube only flare, neutrino flare, let's say in 2014, 2015, is the strongest, the most robust association between neutrino emission and the blazar, with respect to the one in 2017 where it was on mostly temporal. Now the picture that starts to emerge is that there's more and more sources, notably the Seyfert galaxies. So I would say that I'm not convinced, or it's pretty clear that blazars alone cannot explain the neutrino, the bulk of the neutrino flux observed by ice cube. And also the association between blazar flares and neutrino does not seem to be very robust. There's been, during the neutrino flare, the blazar was not flaring in gamma rays. So I think I don't want to bet too much on that, but I would say that the picture is more complex, and there is definitely other sources like Erbert that are a bit more promising to explain the fraction of the neutrino flares seen by the IXPE.
Okay.
Yeah.
One curiosity, at certain point, Magic claimed this bump at around the film TV in the Markarian 5.1, no? You have analyzed quite some data of Markarian. Can you confirm or comment on this bump?
So what I can say is that we did not see it in other spectra.
So it remained like a hint that has
Yeah,
never
yeah.
been seen again.
I think this is where CTA would be very powerful to see sub energy structures in the spectrum. But so far we never saw it again, so it remains a hit. That's 3, 4 sigma. And that's
Yeah.
No question. Online?
So for this type of studies, I suppose, I mean, the CTA north with the